Hello everyone, welcome back to my channel. A boundary or a border can separate two countries. Similarly, a boundary can separate two classes or multiple classes. And throughout this video, we are going to explore that concept in a very understandable manner. And we are going to start with support vector machines concept today. And we will start with the topic right now. Stick to this channel or stick to this video throughout so that you will not miss any single concept related to this. So we are going to talk about SVM or the support vector machine algorithms, and it's a supervised algorithm and it is used for both classification and regression tasks, guys. And what exactly is the main fundamental behind it? It tries to exactly find the best boundary, or which we are calling as a hyperplane, which separates the different classes in the dataset. So in short, I can say that if you have two classes, how it is going to separate, or suppose one new class is getting introduced or one new point is getting introduced, how it is going to understand to which class it belongs. That is the problem statement which it solves, right? If a new point or if set of new points are coming into picture, how it is going to differentiate? This is the concept. It's going to create a boundary first, whatever the existing data points are present, and that boundary, it is going to create a highest margin between those two classes. So the margin again is nothing but a distance between those two classes. Again, for margin, it's going to create some unseen planes or unseen lines, and that margin, it's going to give you the predicted output with that margin. And the points or the dots or the data points which are present near that margin are nothing but your support vectors. So to explain that in better way, let me take you to the whiteboard and show you how exactly it's going to be. So before moving ahead, what we are trying to understand? We are trying to understand support vector machine. And what are the factors it is needed? First is hyperplane. Second is what? Margin. Third, support vectors. Fourth is what? Fourth is my kernel. This is my hyperparameter. So these are the factors, and now we will understand how exactly it works. So for that, if you have two lines, or this is my x1, this is my x2, and these are my, suppose I have two classes. Okay, first if I have star class, and I have triangle. I have two classes, right? Because I have two variables, that means I have two classes. So what exactly it is going to do? It is going to create a plane. Just like this, it is going to create a plane. And this is called my hyperplane or my boundary. Then what exactly it is going to do? It's going to create margins. So this is the highest margin it is going to create. So this is my margin. Then what exactly it is going to do? These points which you are seeing near, right? This one, this one, this one, this one. So these are nothing but my support. Okay, let me just do it in a good way. So these are nothing but your support vector, right? So what we understood? We understood we have a hyperplane, right? We have hyperplane, then we have margins. This is my distance, guys, right? This is my distance. Then we have support vectors. So to handle or to know how these things are behaving, we have a kernel concept, right? And we will explore that part as well when we'll proceed further. Yeah, so that's it, guys. That's it. So we understood the concept. Now we already discussed about these things, right? We have hyperplane, then we have support vectors, margin, kernel, hard margin, soft margin. So what exactly is hard margin and what exactly is soft margin? Because we understood all these points, hyperplane, support vectors, margin, and kernel is nothing but it's the smooth operation, how this SVM is going to handle the data, or how it is going to predict the data in a higher dimensional space in a very smoother way. Kernel function is going to handle that. Then we have hard margin. So hard margin is something like it's again the margin. Margin means what? It's a distance between those two imaginary lines, right? Which it is going to create between the data points, between different classes. So hard margin is something, again, that's a margin in hyperplane. What exactly it is doing? It separates the data without misclassification. That means with hard margin, we will not get misclassified. We will get the correct output according to hard margin. Then if we'll go ahead with soft margin, what exactly it is going to do? Whatever the data points it has, it is going to put, or it is going to insert some misclassification. So there one more point comes into picture, that SVM is really robust for outliers. Even though misclassification, or if you are putting misclassification, how this soft margin is going to work, it's going to penalize that. Okay, if you are predicting wrong output, whenever the moment I am inserting any misclassified input or misclassified data point, it's going to penalize. Still, it's going to give you the correct output. That's the beauty of SVM. And that's the concept of soft margin. So soft margin in short is going like in this concept, we are going to insert some new misclassified input so that we want to know whether it's predicting correctly with those classified output or not, input or not. So to handle that, we have few hyperparameters which we are going to discuss during our real time example. However, those hyperparameters here we are calling that as the C value. One is a C value and one is a slack variable. And to define the loss, we have loss function as well in this, which is getting handled internally. We cannot see anything here. And we will understand now the mathematical intuition of SVM, how it is getting derived mathematically. So what is the goal, guys? What is the goal of SVM? It's going to create a maximum separation between classes by creating different margins, right? So what is a margin? Margin is nothing but the distance between the separating line and the closest point from that classes, from each classes, right? And those closest points to the margins are called your support vectors, right? And what SVM is doing? SVM is trying to push the line farther from those support vectors so that it is going to give you the correct output whenever any new prediction or new predicted input is provided. And how we are depicting that? So we have Wx plus b. That's our fundamental, guys. That's the formula on which your SVM is based on. So here W means it's the weight matrix or weight which you are going to provide for each data, right? And X is your input feature, to the feature where you wanted to apply the SVM. That's nothing but your input feature. B, that's nothing but a bias, or I can say that how much it is going to up or down. That's the point. So this is the equation. Wx plus b is your equation. So how your prediction is happening? If my Wx plus b is greater than 0, that means it's going to be class 1. Suppose you have two classes. You have class plus 1 and class minus 1. So if the output of this wx plus b is coming greater than or equal to 0, that means we are going to consider, okay, that's going to be plus 1 class. If it is less, then we are going to consider that as a minus 1 class. So the concept behind this wx plus b is a formula. Then what we are going to do once we are getting a margin, we understood hyperplane, we understood margin, we understood the mathematical intuition on how SVM works. Now to get more, because we know that the bigger the margin is, the better the prediction is going to be. So to get that big margin or the larger margin between those data points, what support vector machine is going to do, it's going to increase the length of the weight vector. It's going to manipulate the length of the weight vector as much as possible, and this is the formula for that. You don't have to remember these formulas. These are the how, like, I'm just relating these concepts so that you can, like, these things will trigger in your brain. So if your W is smaller, that means if your weight vector is smaller in like the value which you are going to get, that means the margin is larger in that case. So here, now we understood about this. Now we will understand the soft margin. So this is my hard margin in short, or in other case. So what my soft margin is going to do? In real, right? I mean, in real, your data is never like this, right? I mean, if I draw it here, always my data can never be like this, right? If I have two classes, right? My data can never be like this, right? I suppose I have two classes, triangle and circle. So it is not very easy, right? The way we are seeing, is it always the same case? It is not. Our data will look more messier, guys. I mean, if you'll see, in real scenario, the data is something like this. Some places it is getting overlapped. Then, the data is very, it's very messier, guys. So in that case, a simple plane like this won't give you the output. So what exactly the concept comes into picture? We have soft margin for that. So for soft margin, we are, understanding one important hyperparameter. That's nothing but the epsilon, or this symbol which we are talking about. So what exactly it is trying to do? Again, soft margin. Here the agenda or the goal is going to be always to get a big margin, and it's going to find out, or we have one more important parameter, the hyperparameter which we are considering. It's C. So if it is higher, if C value is higher, that means it's going to make less mistake and it's going to be very strict. That means the prediction. If your C value is low, that means more freedom and very smoother boundary. That means it's not, it's going to create a boundary like this. You can see, right? That means it's going to create a boundary like this. If C value is less, it's going to create smoother boundary like this. Else it's going to be very stricter. So in case if your data is, like, in short, how you are going to understand soft margin, that in case if your data is not linearly separable, SVM is trying to understand, or it's trying to understand how the data is getting presented in higher dimensional space using the kernel function. So again, one more concept comes into picture, that's kernel function. So we understood hard margin, soft margin, right? Hard margin, this is the formula. Soft margin, this is the formula. Soft margin, we have few hyperparameters which you have to consider. So one is epsilon, one is C. So if C value is high, that means it should make less mistake. Like we are telling our algo to make less mistake, do not make more mistake. If say C value is more, it's going to create very smoother boundary, and it's going to try to be more intuitive in providing the output. Then now we understood what is the function of kernel, like what is the agenda, or what exactly my kernel function is doing. It smoothens, or it helps to go ahead and understand the classification of different classes in higher dimensional spaces, because every time we are not understanding the data in 2D or in 3D. The more amount of data present, the more number of dimensions it is going to create in space. We don't know that, right? And to handle those kind of scenarios, we have kernel function comes into picture. So we have three types of kernel function. One is a linear kernel, where the data is already linearly separable, and it's good in high dimensional data. Like if you will go ahead with text data, then handling spam emails, because there the words are very, very key to understand how those inputs are behaving among each other. Right? In case of images, so in those cases we are using linear kernel. Then polynomial kernel, again I already explained you how my regression works. During that time, what I told you, we have degree of polynomial. So here also we have degree, then we have C as a constant term. Then here the data is curved, but with smooth boundaries, right? If your data is curved, it's not a linear fashion, and here it is going to create a smooth boundaries as in a part of hyperplane. Then with this we are getting more flexibility of the operation, how it is happening, right? Then we have RBF kernel. RBF kernel, it's called as a Gaussian kernel, and is the default one. If you'll see the SVM, the most important, and it's the default one. What exactly it is happening here? The data points, it's creating a bump or peak around it, right? And the classifier then builds boundaries by combining these bumps. So let me show you that in whiteboard exactly what this concept is saying. If I'll create a data points, again I am taking the same example. Okay, or let me take two different type of points. Okay, so my first point's going to be, so suppose I have these data points. Okay, I have these data points, and one more is going to be my green color. So I have these data points. So I have two different classes. So if I'll take this, this. So what exactly it is going to do? My RBF, it's going to create a smooth curve like this. It's going to start. It's going to create. Okay. Now let me put back in black. It's going to create a smooth curve like this. Let me get a dotted line. A smooth curve like this. So this is my RBF kernel, right? With this, you can see my curve which I am getting is smoother, and this separates my two classes, right? This is my pink class, pink point, and this is my green class, right? So this is how I am able to get my RBF kernel, and RBF kernel is my default kernel in case of your SVF, support vector, not F, SVM. Okay, now we will go back to our PPT. So the same thing I'm saying it here. It's going to, so you can see that from that image, right? It has created bumps around it, like, and it's going to connect the dots. Here in that example, we saw that the data is very messier, right? I mean, a few of the green points are going inside those pink points, and pink points are coming inside the green zones, and RBF is helping to handle those kind of highly nonlinear cases. And we don't know how the structure is going to be, right? And all we are just going with the intuition, with the mathematical intuition of everything. Then we have two different type of SVM, linear and non-linear. So linear SVMs, again, like I already mentioned, those are applicable only for linearly separable data. That means the data do not need to undergo any kind of transformations or anything when we are proceeding, or when a new class is getting introduced. It is not needed to go for the hard transformation process. And what we understood about the hyperplane formula? We have Wx plus B, right? And with that, it's creating a hyperplane, and we are going into the margins, and we are just proceeding with the predictions in case of SVM. So if we are using hard margin SVMs, then the data points are perfectly separated outside of the support vectors. If we are going into soft margin, then it's flexible, it's creating softer boundaries around those data points, and we have slack variable, we have hyperparameter which adjusts those margins, right? And in case of non-linear SVM, so that is linear. In case of non-linear SVMs, what we understood is the kernel trick or the kernel function, right? The kernel function is helping to understand the complexity present in those data points, and it is creating the computation or handling those data points is becoming easier with that. What exactly it is doing? All the metrics when you are understanding in real scenario, those all are dot products. In case of your whole artificial intelligence, we don't know exactly what is happening. To get the margin, to understand, to connect the dots, to get the distance between those dots, everything is a dot product, guys, here, right? So it's just replacing those dot products with the kernel function. So that's all it is doing for getting for achieving the margin. Then we have different pros and cons. For every algo, we have different advantages and disadvantages as well, because everything is not perfect in this world, right? So we have few pros here, like it is very better with high dimensional data, right? And if the data set, like we already saw, that if a data set is it is not linear, or it can handle the non-linear capability of the data set, right? It is very good with outliers. So in case while separating out those data points, if 1 point or 2 point are misclassified in that, it's going to called as outlier, because one class data point is present in another class. That means it's outlier, and it is really easily handling those kind of outliers. It's an outlier resistance algorithm. Then it is supporting for both binary and multi-class, and it's very good in efficiently handling the memory part of your system. And we have few disadvantages as well, because here we are handling, or it can handle the high dimensional data. The training is going to be slower, because it's going to understand a pattern while creating the hyperplane among those data points, right? Because it's not only we are going ahead 2 data points or 2 classes, multiple classes will be there in that, and it is going to create multiple planes accordingly, or multiple SVMs are going to be created inside internally. We don't know that. And here parameter tuning is bit difficult, because here if case of high dimensional data, the training is going to be tough, because you have to, when we're creating different folds, right, when we're going ahead with different hyperparameters, when we're considering C value as a hyperparameter in this case, then we are considering epsilon, all those things, it's difficult to determine. If we'll go with parameter tuning, then it's less effective with noise. If a data set is having high noise or high variance, it's not going to perform well with that. It has limited interpretability. Then feature scaling sensitivity, like it is less effective with feature scaling. That means then we have several real world problems it is solving SVM. Spam detection, right, where we are sensitivity of words are present in those emails. It's going to detect that, and it is going to segregate with spam or not spam. Image classification, then word classification, then sentiment analysis, bioinformatics, financial fraud detection, then geographic information system. In all those scenarios, SVM is really helpful. So we understood the concepts of SVM, guys, and we will meet during our next video with a real world example. So what I'm planning, guys, in throughout this journey, that the algorithms which have both regression and classifier, it's my duty to show both of the things, because none of the other channels are doing that, or none of the other platforms are doing that. However, I'm going to show both classification and regression problems together after each algo, and that's the fashion which I'm going to, or that's the trend which I'm going to follow throughout this ML. So we'll meet during our next video. That is all for now. We will start with the practical or the real world scenarios on how the SVM works, and we will explore during our next videos on that. If you really like the contents, guys, please start subscribing, like, share your comments, share your valuable feedback, and see you till next time. We'll meet during our next video. Thank you. Bye.